Think about all the stuff we do online every day. Banking, shopping, booking flights. Underneath all of that, there's this invisible guardian making sure our data doesn't just turn into total chaos. Today, we're going to pull back the curtain on this unsung hero of the digital world. So let's kick things off with a scenario I'm sure you can relate to. Imagine your favorite band just dropped tickets for their tour. You, and probably thousands of other people, smash that buy button at the exact same instant for the very last seat. What is it that stops the system from selling that same ticket twice, leaving one of you totally bummed out with a useless order? Well, what you're dealing with there is the classic problem of concurrency. It's what happens when a whole bunch of actions try to read and write the same piece of data at the same time. I mean, without a solid system to manage this, you'd have double bookings, your bank balance would be a mess, just a world of data nightmares. So how do databases even begin to solve this puzzle? The answer is a really powerful and fundamental concept called a transaction. Let's break down what that actually means. A transaction is basically the database's way of saying, look, you're either going to do this entire sequence of steps or you're not going to do any of it. It's an all-or-nothing deal, period. There's no halfway. The system just won't accept a partial update. And here's a perfect everyday example. When you buy something, two things have to happen, right? The product quantity in the inventory has to go down, and the balance on your account has to be updated. A transaction wraps these two steps together into one single logical unit. Now what happens if the power cuts out right after step 1 but before step 2? The whole thing gets rolled back. It's like it never happened. The product isn't lost, and you aren't unfairly charged. To make sure these all-or-nothing promises are actually reliable, transactions have to follow a really strict set of rules. You can think of it as their code of conduct. And it's all wrapped up in this super famous acronym in the database world, ACID. These 4 properties, atomicity, consistency, isolation, and durability, they're the pillars that hold up all of trustworthy data management. So let's break down what each of these really guarantees for your data. First up, we've got atomicity. This is that all-or-nothing principle we were just talking about. Just think of it like this. You're putting all the steps of your transaction into a sealed envelope. Either every single step inside that envelope gets done perfectly, or the whole envelope gets tossed in the trash. It's indivisible. Next is consistency. This one makes sure a transaction can only take the database from one valid state to another valid state. For example, let's say a rule in your database says inventory can't go below 0. Well, if a transaction tries to sell a product that's out of stock, it would violate that rule. So the system just rejects it, making sure the database's rules are never, ever broken. Then there's isolation. Now, this is the one that solves our concert ticket problem from the beginning. It makes sure that while one transaction is busy doing its thing, other transactions can't see its incomplete work. Each one operates in its own little bubble, which makes it seem like they're all happening one after the other, not all at once. This is also known as serializability. And finally, durability. This is the ultimate promise. Once the database gives you the thumbs up and says a transaction is committed, that change is permanent. It's carved in stone. These changes are written to something called a transaction log, so they'll survive a power outage, a system crash, pretty much anything. Your money transfer is safe. Okay, so we've got these amazing ACID guarantees, but you might be wondering, how on earth does a database system actually enforce all this when you've got thousands of transactions flying around at once? Well, the answer is a feature called concurrency control. There's a little component in there called a scheduler, and it acts like a traffic cop for the database, directing the flow of all these transactions to make sure they don't crash into each other and mess up the data. Its whole job is to uphold that isolation promise we just talked about. And the main tool this traffic cop uses is the lock. It's really simple, actually. When a transaction needs to mess with a piece of data, it puts an exclusive lock on it. It's just like putting a do not disturb sign on a hotel room door. No other transaction can come in and change things until the first one is done and takes the lock off. Now, systems have basically 2 different mindsets here. On one hand, you've got pessimistic locking. This approach is, well, pessimistic. It assumes there's going to be a conflict, so it locks data right away. It's super safe, but it can make other users wait. On the other hand, you've got the optimistic approach. This one assumes conflicts are rare, lets transactions do their work, and only checks for a collision at the very end. It's way faster, but if a conflict does happen, the transaction fails and has to start all over. So Locks are a brilliant solution, right? But like any good solution, they can create their own, shall we say, unique set of problems. This can lead to a really frustrating problem called a deadlock. It's basically a digital standoff. Imagine two people meeting in a super narrow hallway. Each one is waiting for the other to move, but neither of them will budge. In a database, two transactions can get stuck in the exact same way, waiting forever for a resource that the other one is holding. All right, let's walk through how this actually happens. You have transaction A. It swoops in and puts a lock on the product data because it needs to update the inventory. Next, it needs to update the customer's balance, so it asks for a lock on the customer data. Okay, but here's the kicker. At the exact same moment, transaction B has already locked the customer data to, say, check a balance, and now it's waiting for the product data to check a price, and we're stuck. A is waiting for B, and B is waiting for A. Neither one can move forward. They're deadlocked. Now, thankfully, database systems are pretty smart. They're not just going to sit there forever. They have strategies to deal with this. They can try to prevent deadlocks from ever happening or detect them when they do. But a lot of the time, the simplest solution is to just pick one transaction as the victim, shut it down, and roll it back. That frees up the other one to finally finish its job. So when you pull it all together, it's pretty clear that transaction management is one of those critical, invisible forces holding our digital world together. From the ACID properties that give us reliability to the concurrency controls that manage all the chaos, these systems are working around the clock to keep our data safe and consistent. And that kind of leaves us with a big question for the future, doesn't it? I mean, we live in a world of global databases, cloud computing, and billions of requests happening all at once. These principles we've talked about are more important now than ever. The question is, as our systems get even more complicated, what's going to be the next big challenge for making sure our data stays safe, consistent, and correct?